Right then, let's dive straight in. Welcome back to the deep dive.
Hello again.
This time we're carrying on with our GCSE Computer Science series, episode 7 now, I think, and we're tackling computer networks. Really fundamental stuff.
Absolutely. It's basically understanding how all your devices, your phone, your computer, the school PCs, how they all connect and, talk to each other.
Yeah, the hidden connections.
Exactly. We're going to break down the core ideas. We'll look at the different types of networks, LANs, WANs, then wired versus wireless connections.
Like Wi-Fi and cables.
Spot on. And how LANs are actually laid out, topologies we call them, plus the rules they follow, the protocols, keeping things secure, and this idea of layers, which helps manage it all.
So if you've ever wondered why the internet seems slow sometimes, or just how your console connects for online games, this should give you a good grounding. It's all around us, this tech.
It really is. So let's start right at the beginning. What is a network?
Good question. Simply put, it's just, well, two or more devices that are connected so they can share things. Resources, data, that kind of stuff.
Right. And for your GCSE, there are three main types you really need to get your head around. First up, the LAN.
Okay, LAN, local area network. Sounds small, and it is. Usually covers a small area, like maybe under a mile. Think your home network or the network in your school IT suite, maybe a small office.
And a key point for LANs is that the hardware, the cables, the switches, the Wi-Fi boxes, it's typically owned by whoever runs the network, like the school or you at home.
Yeah, and connection methods are usually things like standard network cables, Ethernet, or maybe faster fiber optic, or just plain old Wi-Fi.
Spot on. So that's the local picture. Then we zoom out to the wide area network, the WAN.
Right, much bigger, covers a large geographical area, basically anything over a mile. A WAN is often made up of lots of different LANs connected together, isn't it?
Exactly. Think of the internet itself as the ultimate WAN. It connects LANs across cities, countries, the whole world. And we use devices called routers to link these networks.
And unlike a LAN, you don't usually own all the WAN infrastructure yourself.
No, definitely not. The cables running under the streets or the satellites, that's usually owned by telecom companies or internet service providers. They use things like fiber optic cables, maybe older telephone lines, even satellite links to cover those huge distances.
So LAN is like your house network. WAN connects towns and cities. Got it. What's the third type?
The third one is the personal area network, or PAN. This is really short range.
Ah, like Bluetooth.
Precisely. We're talking maybe up to 10 meters maximum. It's for connecting devices that are super close together. Wireless headphones to your phone, a controller to a console, your phone to your laptop for a quick file transfer, that's a PAN.
Okay, that makes sense. LAN, WAN, PAN, different scales for different needs. So why bother setting up networks at all? What are the plus points?
Oh, loads. The big one is sharing resources. Think about printers. Instead of every computer needing one, you can have one printer shared by everyone on the network.
Saves money. Same for the internet connection, right? One broadband line serves the whole school or house.
Exactly. And accessing files becomes easier. You can often log in from any computer on the network and get to your saved work, maybe stored on a central server.
Communication too, email, messaging apps, social media, they all rely on networks. And sharing files like spreadsheets or databases is much simpler.
Definitely. And from an admin point of view, if you have servers, you can manage things centrally. Backups can be done in one go, software updates pushed out easily, and security managed from a single point. Makes life easier for the IT support folks.
Okay, sounds pretty useful, but are there any downsides, any drawbacks to having everything connected?
Yeah, there are a few things to watch out for. Security is a big one. The more connected things are, the more potential entry points there are for, well, hackers or malicious software.
So like a virus could spread more easily across a network.
Exactly. If one machine gets infected, it can potentially spread to others much quicker than if they were all standalone. That's a real risk.
Okay. What else?
Well, you can have single points of failure. If a really important piece of kit, like the main server where everyone saves their work, or a central network switch, breaks down,
Then everyone connected to it is stuck. Yeah, I can see that.
it can cause major disruption. And finally, performance can sometimes be an issue. If you've got loads of people using the network heavily at the same time, streaming video, downloading huge files, it can slow down for everyone. Think about school Wi-Fi at lunchtime.
Aha. Yeah, tell me about it. Okay, so networks have pros and cons. Now, how do we actually connect these devices? You mentioned wired and wireless earlier. Let's start with wired. That's using physical cables, yeah.
That's the one. Actual physical wires linking devices. The most common type you'll see, especially in schools and offices for LANs, is Ethernet cable.
Those plastic-coated cables with the clicky ends.
That's them. Inside, they've twisted pairs of copper wires. They allow for something called duplex communication data. It can travel both ways at the same time, which is efficient.
Okay, Ethernet. What else? You mentioned fiber optic?
Ah, yes, fiber optic. This is the really fast stuff. Instead of electrical signals down copper wires, it sends data as pulses of light down thin strands of glass or plastic.
Light speed data.
Pretty much. It's mainly used for the backbone of WANs connecting cities or countries, but sometimes in LANs where you need serious speed. The big pluses are incredible speed and bandwidth. It can carry way more data than copper.
And it's more secure, you said.
Yeah, because it uses light. It's not susceptible to electrical interference like copper cables can be. And it can send data over very long distances without the signal degrading much.
Sounds great. What about just plain old copper cable, like telephone lines?
Well, traditional copper telephone lines were the original infrastructure for networks, especially for getting the internet into homes via DSL over the WAN. They did the job, but they have limits.
Like,
They degrade over distance, so the signal gets weaker. They're much more prone to interference, which can corrupt data. And compared to fiber, their speed and bandwidth are significantly lower. They're being replaced by fiber in many places now.
okay, so 3 main wired types. Why choose wired then? What are the advantages?
Generally, you get faster, more stable speeds than wireless. It's usually considered more secure because someone would need physical access to tap into a cable. The range is pretty decent, maybe up to 100 meters for Ethernet, and it's less prone to interference from other devices or walls.
But the downsides.
Portability, mainly. You're tethered by the cable.
Yeah.
Adding a new device means running another cable, which can be costly or messy. And yeah, cables trailing across floors can be a trip hazard.
Definitely tripped over a few network cables in my time. Okay, so that's wired. What about wireless? No cables involved here.
Correct. Wireless networks use radio waves to send data through the air. The main type everyone knows is Wi-Fi.
Our beloved home Wi-Fi.
Exactly. It's the common standard used in homes, schools, cafes, offices. Allows your laptop, phone, tablet to connect to the network wirelessly. Devices talk to a wireless access point, or WTP.
Which is often just built into the router box the internet provider gives you.
Often, yes. Or it might be a separate box connected to the network switch in a larger building. And remember, Wi-Fi is technically a brand name. The generic term is Wireless Local Area Network, or WLAN.
Ah, good point. WLAN. And the other main wireless type.
Bluetooth, we mentioned it with PANs. It's those short-range, direct connections between two devices, headphones, keyboards, mice, game controllers. Very handy for peripherals.
So, wireless advantages. Why ditch the cables?
Freedom. Portability is the big one. You can wander around with your laptop within the signal range. It's often cheaper and easier to add new devices, no extra cables needed. And pretty much every modern phone, tablet, and laptop has Wi-Fi and Bluetooth built in.
But it's not perfect, right? What are the drawbacks?
Generally, speeds can be slower and less consistent than a good wired connection. Security can be more of a concern because the signals are traveling through the air, potentially interceptable. And the range is limited by distance, walls, other obstructions, maybe up to 90 meters for Wi-Fi, but often less indoors.
Okay, wired for speed and stability, wireless for convenience and portability. Makes sense. Now let's loop back to LANs, those local networks. How are they physically arranged? You called it topology.
That's right, network topology. It's the map or layout of how the devices and cables are connected. The most common one you'll see today is the star topology.
Star. How does that work?
Imagine a central point, usually a device called a switch, and all the computers and other devices connect directly to that central switch with their own cable, like rays coming out from a star.
Okay, a central hub. Well, switch.
Yeah, exactly, a switch. And it's quite clever because it learns which device is connected to which port. So when data comes in for a specific computer, the switch sends it only down that computer's cable, not to everyone.
Efficient. Where would we find star networks?
Pretty much everywhere now for LANs. Homes with multiple wire devices, definitely schools, businesses. It's the standard, really.
What's good about it?
Well, if one cable breaks, it only affects the one device connected to it. The rest of the network carries on fine. Makes it easier to find and fix problems, too. You just check the connection between the device and the switch.
Sounds robust. Any downsides?
The main one is that central switch. It's a single point of failure if the switch itself dies.
Everyone connected to it loses their network connection. Ouch.
Yep, That's the main vulnerability.
Okay, star. What was the other one you mentioned? Bus. Sounds old-fashioned.
It is really. Bus topology isn't used much for new LANs. But the idea was you had one single main cable, the bus running through the area, and all the devices tapped into that same cable.
Like stops on a bus route.
Kind of. And there were special plugs called terminators at each end of the main cable to stop the electrical signals bouncing back and causing interference.
How did devices know which data was for them?
Basically, every packet of data sent on the bus had an address. Each device would listen to all the traffic passing by, check the address, and if it matched its own, it would grab the data. If not, it ignored it.
Why don't we use it anymore then?
It had some significant problems. Security wasn't great because technically every device could hear all the data traveling on the bus. Performance was often poor, especially if lots of devices tried to send data at once. You'd get collisions, like cars crashing on a single-lane road.
Data crashes.
Exactly. And that main bus cable was a massive single point of failure. If that cable broke anywhere along its length, the whole network segment would stop working.
So star is generally much better.
Much more reliable and efficient, yes.
Right.
Bus was cheaper and simpler to cable initially, which is why it was used, but star won out in the long run.
Right, so we have the physical layout, but how do devices actually, speak the same language when they send data? That's protocols, isn't it?
Precisely. A protocol is just a formal set of rules and conventions that governs how data is formatted, transmitted, and received between network devices. Without agreed protocols, devices wouldn't be able to understand each other.
Like having rules for how you address an envelope so the postman knows where to take it?
That's a great analogy. Protocols ensure everything is structured correctly for communication. And there are protocols for different jobs. We've already touched on Ethernet and Wi-Fi.
Yeah.
There are really families of protocols that define how data is transmitted over wired and wireless LANs, respectively.
Okay, LAN protocols. What about for the wider internet, the WANs?
The absolute cornerstone there is TCP/IP. It actually stands for two core protocols bundled together, TCP and IP.
Transmission control protocol and internet protocol.
You got it. TCP's job is primarily about ensuring reliable data transfer. It breaks data down into packets, numbers them, makes sure they all arrive at the other end, checks for errors, and reassembles them in the correct order. It manages the flow of data between 2 points, like routers.
So TCP makes sure the message gets through intact. What about IP?
IP, the Internet Protocol, is all about addressing and routing. Every device on the Internet needs a unique IP address, like a postal address. IP is responsible for adding these addresses to the data packets and figuring out the best path to send them across the vast network of the Internet to reach the right destination device.
So TCP handles the reliability, IP handles the delivery address, put them together, and you get internet communication.
That's the heart of it, yes. TCP/IP is fundamental.
Is there an alternative to TCP for sending data?
Yes, there's UDP, User Datagram Protocol. It's also used for sending packets over WANs, but it's different from TCP. UDP is much simpler and faster because it doesn't bother with all the error checking and guaranteed delivery stuff that TCP does.
Faster, but less reliable. Why use that?
Sometimes speed is more important than perfect accuracy. Think about live video streaming or online gaming. If a few packets get lost, it might cause a tiny glitch, but it's better than having the whole stream pause while TCP waits for a lost packet to be resent. So UDP is used where some data loss is acceptable.
Okay, TCP/IP for reliable internet, UDP for speed. What about when we're browsing websites?
That's where HTTP and HTTPS come in. HTTP is the Hypertext Transfer Protocol. It's the set of rules that your web browser uses to request web pages and associated files, like images, from a web server and for the server to send them back.
And HTTPS.
The S stands for secure. HTTPS is just HTTP, but with an added layer of encryption, usually something called TLS or SSL. This scrambles the communication between your browser and the server, making it safe to send sensitive information like passwords, credit card details, personal info. You'll see HTTPS on banking sites, online shops, login pages, anywhere. Security is important.
Always look for the padlock icon.
Definitely. Then there's FTP File Transfer Protocol.
For transferring files. Makes sense.
Exactly. It's specifically designed for uploading and downloading files between computers, often used for managing files on web servers or transferring large data sets. It's efficient for bulk transfers and can often resume an interrupted download. You usually use special FTP client software to connect to an FTP server.
Right. And finally, email. Different protocols again?
Yep, mainly two you need to know, SMTP and IMAP. SMTP, the Simple Mail Transfer Protocol, is primarily used for sending email, When you hit send in your email client, SMTP is used to get the message to your mail server, and then SMTP is used between mail servers to route the email across the internet to the recipient's mail server.
So SMTP is for the outgoing journey. What about getting email?
That's usually handled by IMA, the Internet Message Access Protocol. When your email client checks for new mail, it uses IMA to connect to the server and download messages. A key feature of IMA is that it typically leaves a copy of the email on the server, allowing you to access the same mailbox from multiple devices, your phone, your laptop, webmail, and see the same emails everywhere.
Ah, okay. So lots of different rules for different jobs. It's amazing it all works together.
It is complex. Which
Okay.
brings us nicely onto security. With all this data whizzing around, keeping networks and the information on them safe is crucial, especially as we store more and more sensitive stuff online.
Yeah, you hear about data breaches and hacking all the time. So how do we protect networks? What are the main methods?
Well, first up is authentication. This is all about verifying that someone or something is who they claim to be before granting them access.
Like logging in with a username and password?
That's the most common example. But credentials can also be things like physical ID badges to open doors in a secure
Yeah.
building, special access codes, or even biometrics, fingerprint scans, facial recognition. It's the gatekeeper function.
Okay, proving you are who you say you are. What else?
Encryption is vital. We touched on it with HTTPS. It's the process of scrambling data so that even if someone intercepts it, they can't read it without the correct key.
Turning plain text into secret code.
Essentially, yes, using complex mathematical algorithms. Asymmetric encryption, using public and private keys, is common for things like secure websites. It protects data while it's in transit across the network.
So authentication checks who you are, encryption protects the data being sent. What about stopping unwanted traffic getting in?
That's the job of a firewall. Think of it as a security guard or a filter standing between your private network, like your home or school network, and the public internet.
How does it work?
It inspects the data packets trying to come into or leave the network, checks them against a set of predefined security rules, and blocks anything that looks suspicious or isn't allowed.
Can you get different types of firewalls?
Yes, you can have hardware firewalls often built into routers which protect the entire network. And you can have software firewalls running on individual computers protecting just that machine. Using both often provides the best protection.
Hardware for the gate, software for the individual doors.
Good way to put it.
Yeah.
And one more technique, especially common on Wi-Fi networks, is MAC address filtering.
MAC address. What's that?
Every network card, wired or wireless, has a unique physical address burned into it by the manufacturer called a Media Access Control MAC address. It's like a serial number for that specific piece of hardware.
Okay, a unique ID for the network adapter. How does filtering help?
You can configure your router or wireless access point with a list of the MAC addresses of devices you trust. This is called a whitelist. The router will then only allow connections from devices whose MAC address is on that list.
So even if someone knows the Wi-Fi password, if their device's MAC address isn't on the list, they can't connect.
Exactly. Or you could use a blacklist to specifically block certain known devices. Whitelisting is generally more secure, though harder to manage if you have lots of visitors needing access. It adds another layer of security based on the physical device itself.
Right. Authentication, encryption, firewalls, MSC filtering, key security tools. Okay, we've covered, well, a lot. Network types, connections, layouts, protocols, security. It feels quite complex when you list it all out.
It absolutely is. There are many moving parts, and that's why the concept of layers is so important in networking. It's a way to manage all this complexity.
Layers, like layers of a cake.
Sort of. Think of breaking down a really big, complex task, like sending an email across the world, into a series of smaller, more manageable subtasks. Each layer handles one specific part of the overall job.
Makes sense. Divide and conquer.
Precisely. It makes the whole system easier to design, build, troubleshoot, and update. The most famous model using layers is the TCP/IP model we keep mentioning. It uses a stack of 4 layers.
What are the advantages of doing it this way with layers?
A big one is modularity. Each layer is relatively self-contained. You can change how things work within one layer, maybe update a protocol or switch from wired to wireless at the bottom layer without having to redesign all the other layers.
So you could swap out Wi-Fi for Ethernet without changing how your web browser works at the top layer.
Exactly. It promotes interoperability too. Different companies can make hardware or software for a specific layer, and as long as they follow the rules for how that layer interacts with the ones above and below, it should all work together.
Okay, so it makes things more manageable and flexible. What are the 4 layers in the TCP/IP model then?
All right, let's go top to bottom. Layer 4, the top one, is the application layer. This is the layer that interacts directly with the software applications you use, your web browser, your email client, FTP software. Protocols like HTTP, HTTPS, SMTP, IMA, FTP all operate here.
So this layer talks to the programs we actually see and use. What's next?
Layer 3 is the transport layer. Its main job is managing the communication session between two devices across the network. It handles things like segmenting the data from the application layer into packets, ensuring reliable delivery if needed, and controlling the flow of data. This is where TCP and UDP live.
Okay, transport handles the end-to-end connection reliability and flow. Below that.
Layer 2 is the internet layer. This is all about addressing and routing. It takes the packets from the transport layer, adds the IP addresses, source and destination, and figures out the best path to send the packets across the internet network. The main protocol here is, unsurprisingly, IP.
The logical addressing and pathfinding layer. And the bottom.
Layer 1, the bottom layer, is the link layer, sometimes called the network access or network interface layer. This deals with the physical network itself. It handles how data is actually put onto the physical cable, like Ethernet, or transmitted over the air, like Wi-Fi. It involves the network interface card, in IC hardware, and the device drivers in the operating system. This is where MC addresses are used.
So application talks to apps, transport manages the connection, internet handles addressing and routing, and link deals with the physical sending and receiving.
That's a pretty good summary. And different protocols slot into these different layers to perform their specific functions. It's a really elegant way to structure something so complex.
Phew. Okay, so I think that covers the main fundamentals we wanted to hit today.
Yeah, quite a journey. We've gone through network types, LAN, WAN, PAN, wired connections like Ethernet, fiber, copper, and wireless like Wi-Fi and Bluetooth.
Then LAN topology star and the older bus. Loads of essential protocols, TCP/IP, UDP, HTTP, HTTPS, FTP, SMTP, IMAP.
Don't forget security, authentication, encryption, firewalls, MSC filtering, and finally, tying it all together with the concept of layers using the TCP/IP model as our example.
It's a lot to take in, but hopefully breaking it down like this helps. Understanding these basics is really key for anyone studying computer science. You see this stuff everywhere once you know what to look for.
Absolutely. And maybe a final thought for you to ponder. Think about all the different devices you use just in one day that connect to a network, your phone, maybe a smartwatch, TV, games console, school computer. How do all the concepts we've talked about today, the layers, the protocols, the connections, actually allow them all to communicate and work together, often seamlessly?
Yeah, it's pretty amazing when you stop and think about the complexity hidden behind clicking a link or sending a message. Definitely something to mull over. Right, that's all we have time for on this deep dive. Thanks for joining us.
Thanks, everyone. See you next time.